the anticipation is tangible. In recent decades, we have discovered that chemistry is a universal phenomenon and that distant worlds are abundant. The Earth teems with life in every corner. In this world, evolution has produced beings cognizant of their position in the universe and initiating their foray into space. It seems improbable that this is the sole instance and location in the universe where biological processes have led to intelligence and technology, and it is unlikely that we are the only organisms to have engaged in space exploration and interstellar communication. Astrobiology presents a compelling inquiry. Are we alone in the universe? Envision a young girl seated in a diminutive sandbox. She raises her finger before her nose and examines the grains of sand one by one. Each constitutes a meticulously structured, diminutive universe. One is a lustrous and faceted quartz crystal. Another is a black basalt chip. A blue and opalescent hue characterizes 1/3. Envision that each village and town globally is interspersed with 100 sandboxes. These sandboxes resemble galaxies within the universe. The quantity of grains of sand in numerous sandboxes approximates the number of stars in the universe. We are the young girl, examining adjacent planets within our galaxy, one at a time. Envisioning the biological creations across numerous worlds is a formidable challenge. Inspired by the abundant elements of time and space, physicist Enrico Fermi audaciously inverted the preceding inquiry. He presumed that ample time and opportunity existed for any advanced civilization to explore the galaxy, prompting him to ponder, where are they? In circumstances of insufficient information, numerous potential responses exist to this inquiry, and our interpretation of these responses often reveals more about our perspectives than about the universe itself. Irrespective of our interpretations of the probabilities concerning life, intelligence, and technology in other realms, the universe exhibits remarkable properties that facilitate the formation of heavy elements and the longevity of stars. The framework of physics contains numbers that are meticulously calibrated and conducive to the emergence of carbon-based life forms. Are these facts inconsequential, because we can only perceive a universe with characteristics that permit our existence? Is there a more profound significance? To articulate our ignorance, radio astronomer Frank Drake devised a straightforward equation to summarize our anticipations regarding intelligent life in the universe and the potential for communication. The Drake equation encompasses factors that vary from precisely quantified astronomical metrics, such as the star formation rate in the galaxy, to conjectural elements, including the duration of an advanced civilization's communicative phase. Unfazed by the ambiguity, sure, scientists are monitoring for artificial signals emanating from space. The pursuit of extraterrestrial intelligence, SETI, exemplifies our profound curiosity regarding cosmic kinship. Currently, we are aware of only one location in the universe that harbors life. Scientists are increasingly convinced that the abundance of life on Earth indicates that numerous biological experiments will be conducted. The universe could be abundant with microbial life. A portion of these experiments will yield advanced organisms capable of exploring space and understanding their position in the universe. The inquiry into our solitude depends entirely on whether that fraction is substantial or negligible. If it is not insignificant, we encounter the dichotomy presented in the chapter's epigraph, articulated in slightly altered terms by the science fiction innovator Sir Arthur C. Clarke. Two possibilities exist. Either we are alone in the universe or we are not. Both are equally frightening. The response of fear is justifiable. We are an inexperienced species, uncertain of our identity, and cautiously exploring the cosmos. Recently, we transitioned from an era of hunting and gathering, and we continue to harbor a fear of the night. We assert our confidence as a species in our scientific endeavors, which will ultimately determine whether we reside in a biological universe. In the summer of 1950, Enrico Fermi was proceeding to lunch accompanied by several colleagues. The men were deliberating two narratives that had captivated the nation's newspapers for months: the vanishing of trash can lids and a series of UFO sightings. Fermi humorously suggested a correlation between the two phenomena. After discussing various topics for some time, Fermi suddenly inquired during a lull in the conversation, "Where is everyone?" His colleagues promptly recognized that Fermi was referring to extraterrestrial visitors. They also conjectured that the inquiry was more profound than it seemed. Fermi was one of the foremost physicists in history. Recipient of the Nobel Prize in 1938, he excelled as both a theorist and an experimentalist, and his judgment was so infallible that his peers referred to him as the Pope. Fermi tackled intricate scientific issues by breaking them down into components and performing rapid mental calculations to derive an approximate solution. Fermi questions are essential in the education of scientists. Fermi did not document his reasoning, yet we can infer it. The reasoning remains as sound as it was previously. Unless the solar system is unique, numerous Earth-like planets exist near some of the billions of stars in the galaxy, with a subset potentially harboring life. With sufficient time, life on certain planets will develop intelligence and technology. By a modest extrapolation of existing technology, we will achieve travel at roughly 1% of the speed of light. At that velocity, it requires merely 10 million years to traverse or colonize the galaxy, assuming that travelers do not tarry and proceed rapidly to new worlds. That constitutes a minuscule portion of the galaxy's age and that of its oldest stars. There has been sufficient time and opportunity for extraterrestrial civilizations to engage in communication or visitation, yet we observe no evidence of their existence. Where are they located? This dilemma is referred to as the Fermi paradox, as we do not observe phenomena that we might anticipate. Many individuals, including numerous scientists, typically exhibit one of two instinctive responses to Fermi's paradox. Individuals either posit, there must be an abundance of life in the universe, and numerous civilizations have likely advanced beyond our own, resulting in a galaxy teeming with extraterrestrial beings. Or they assert, that notion is implausible. Intelligence is infrequent on Earth and is likely to be scarce elsewhere, and the vastness of space significantly diminishes the probability of alien contact. Which perspective is more rational? Before exploring potential responses to Fermi's inquiry, let us analyze the essence of the argument. This is an atypical proposition. Science examines observed phenomena and subsequently seeks to elucidate them. In this instance, we are addressing the oversight of an observation. The paradox arises from three statements, each of which appears plausible. Firstly, extraterrestrial beings capable of communication and interstellar travel exist or have existed historically. Secondly, had they visited our planet, we would have observed them. Third, we have not observed them. We will refer to extraterrestrial beings as ETs. It all depends on the initial assertion. If extraterrestrials have never existed, the contradiction between the second and third statements vanishes. We are the inaugural spacefaring civilization. This conclusion acknowledges the Fermi paradox literally. However, disproving the initial assertion would be exceedingly challenging due to the immense expanses of space where extraterrestrial beings may exist. If extraterrestrials exist, then the focus shifts to the subsequent assertion. Numerous credible explanations exist for the potential existence of extraterrestrial beings that may refrain from communication or elude detection, thereby rendering the second statement possibly erroneous and circumventing the contradiction. If the third statement is false and we have encountered extraterrestrials, then the paradox dissipates completely. In this complex landscape, where evidence is limited, we must exercise meticulous caution in our reasoning. Claiming, "I haven't observed extraterrestrials, therefore they likely do not exist," is fallacious, as the criteria for demonstrating the non-existence of entities in a vast and intricate universe are exceedingly stringent. However, asserting the preceding argument is invalid, therefore extraterrestrial beings likely exist, is also fallacious. We lack justification to be astonished by the absence of extraterrestrial contact unless we possess a logical basis for their existence and a reasonable anticipation of their communication. The most straightforward option, supported by a majority of the U.S. population, is the refutation of the third assertion. Extraterrestrial beings exist and have already established contact. Influenced by reruns of The X-Files and Star Trek, along with the prevalence of science fiction in popular culture, the majority of Americans are persuaded that UFOs represent instances of extraterrestrial visitation. Numerous individuals contend that an obscure conspiracy among high-ranking military and government officials has maintained this secret for over 50 years. 3. The literature on UFOs, ancient astronauts, and alien abductions is extensive, allowing only a minimal contribution to the vast realm of speculation. The history of UFO sightings is enlightening nonetheless. 1 century ago, UFO sightings were influenced by the fiction of Jules Verne, manifesting as flying airships and galleons. The modern UFO era commenced in 1947 with a sighting by pilot Kenneth Arnold in Washington state, subsequently followed by the notorious Roswell incident. These UFOs resembled streamlined metallic flying saucers, a cutting-edge technology of the era. Individuals continue to report sightings of flying saucers. However, after 5 decades, these observations appear to have stagnated, depicting technology that seems outdated and rudimentary, bordering on the absurd. When a UFO is identifiable, it typically corresponds to Venus, an aircraft, or a high-altitude weather balloon. Visual observations are inherently unreliable, and in the era of digital photography, an image alone is insufficient for conclusive determination. Fermi dismissed this possibility with his quip regarding garbage can lids. However, even after eliminating all conventional explanations, delusions, and frauds, a persistent residue of cases with credible eyewitness testimony remains difficult to dismiss. Are these genuine visitations? Scientists find themselves in a challenging predicament regarding UFOs. Numerous individuals believe that astrobiological evidence indicates a significant abundance of habitable planets throughout the galaxy, suggesting a substantial likelihood of intelligent life existing beyond Earth. However, they remain entirely unconvinced by the evidence about UFOs. The prudent stance is to demand a rigorous standard of evidence. Photographs, eyewitness accounts, and nebulous conspiracy theories are inadequate. Carl Sagan stated, "It is beneficial to maintain an open mind, but not so open that your intellect escapes." What accounts for the fervent belief in UFOs among specific individuals? Planetary scientist David Grinspoon explored this inquiry by engaging with the enemy, visiting UFO sites, examining the peculiar phenomenon of cattle mutilation, and conversing with individuals who assert they are alien abductees. He has articulated with eloquence the pervasive bubble of belief that envelops and sustains this culture, a realm where skepticism and critical thought are scarce. The assemblies exhibit an evangelical zeal. Grinspoon expresses disappointment that the narratives are somewhat substandard, akin to B-grade science fiction. Physicist Richard Feynman articulated succinctly, "The first principle is that you must not deceive yourself, and you are the most susceptible to deception. There are likely profound psychological motivations behind our desire to believe in extraterrestrial life." In Western culture, extraterrestrials serve as shape-shifting metaphors for the inherent maladies within humanity. UFOs are depicted in medieval paintings and tapestries, as well as within the Christian tradition. Numerous archetypes were integrated into the seminal 1956 science fiction film Invasion of the Body Snatchers. This narrative of extraterrestrial pods that duplicate and supplant humans in a small Californian town served as a subtle critique of the paranoia instigated by Senator Joseph McCarthy and his anti-communist purges. The film encapsulated the conflict between individualism and unthinking conformity, depicting individuals as peas in a pod who yield to mindless uniformity. Conspiracy theories perpetuate a uniform mentality. On the surface, it is comforting to believe that the government shields us from the vast implications of extraterrestrial contact, or that a clandestine military-industrial consortium controls global affairs. Conspiracy theories epitomize the complete relinquishment of personal accountability. If you abandon your critical faculties, you have effectively aligned yourself with the pod people. Such ideas persist due to their self-reinforcing nature. Facts that conform to the theory are accepted. Facts that do not conform are disregarded. This is not merely unscientific, it is anti-scientific. Let us temporarily dismiss the possibility that extraterrestrial beings exist and that the evidence is readily apparent. Let us contemplate the contrary response to Fermi's inquiry. They exist, yet they have never made an appearance. We re-examine the concept of space exploration and colonization. The energy demands for interstellar travel approaching the speed of light are prohibitive. What if we opt to dispatch robots to the stars instead of fragile, short-lived humans? The convergence of multiple technologies indicates a compelling prospect: the replication of space probes. Miniaturization and novel propulsion technologies will enable us to propel small spacecraft to approximately 1% of the speed of light. A swiftly advancing technology facilitates the production of three-dimensional components through programmable machinery. The outcome is swift galactic exploration. 5. This is a potential operational framework. A civilization akin to ours dispatches robotic probes to the closest stars. They investigate planets for indications of life and subsequently extract resources from asteroids or rocky moons to create replicas of themselves. The replicas disperse to a new array of stellar systems, and the cycle recommences. Traveling at 1% of the speed of light, the probes would require merely 1 million years to traverse the entire galaxy. They could transmit their findings to their home planet at the speed of light. A civilization has had billions of years to develop this capability before our existence. What justifies our position as the inaugural entity? In this situation, communication may occur despite the rarity of extraterrestrial life. Only one is required. This can be identified as an alternative manifestation of the mediocrity principle. Why should we be the only children in the neighborhood or the most intelligent ones? However, observe the underlying assumptions. To be astonished by our lack of visitation, one must presuppose the existence of extraterrestrial beings, their capacity for interstellar travel, their decision to refrain from communication or space exploration, and our inability to detect them if they were present. If any segment of that logical chain is flawed, we cannot be sure that we are the only ones. A variant of the rare Earth hypothesis may be accurate. Terrestrial planets possessing sufficiently stable conditions for the emergence of complex life forms constitute a negligible fraction of all planets. Microorganisms are prevalent. However, the constraint lies within the brain. In 4 billion years of evolution on Earth, only a few species have attained a significant level of intelligence. Intelligence may not frequently result in technological advancement and the ability to explore space. Consider the constraints of dolphins and orcas. Exploring alien sociology reveals numerous possibilities. Extraterrestrial beings may travel extensively, yet opt to remain undisclosed to humanity, a concept known as the zoo hypothesis. Many civilizations may self-destruct before achieving the necessary technological advancements for space travel. Exploration may be a cultural phenomenon unique to humans, while intelligent species elsewhere may not perceive a necessity to traverse space. It is possible that extraterrestrials do not traverse space, but instead communicate through methods that elude our comprehension or recognition. It is conceivable that extraterrestrial beings are so peculiar that we would fail to recognize them even if they were nearby. Perhaps the most vexing to our self-esteem is the notion that they visited and deemed us unworthy of attention. The vast age of the universe implies that if we are not the inaugural intelligent and technological civilization, others may possess a considerable advantage over us. Imagine a scenario in which astronauts explore a planet resembling Earth. While traversing its desolate terrain, they document their disillusionment in their space log. Lichen and bacterial colonies are unremarkable. Likewise, if we were to time travel to Earth 1 billion years ago, we would encounter no life form exceeding the size of a pinhead. What if extraterrestrial beings are capable of visiting and have indeed visited, yet possess significantly greater advancements than humanity? What if aliens are to us what we are to bacteria? Fermi's inquiry unveils a myriad of unbounded possibilities. We unequivocally acknowledge that biology is merely one of the phenomena present in the universe, akin to comets, black holes, and quasars. What if life assumes a more pivotal role? What if life is intricately linked to the cosmos, of which it is a minuscule component, suggesting that we, and possibly extraterrestrial beings, are an inherent aspect? We are prompted to consider this bold proposition upon observing specific coincidences in nature. Physics encompasses critical and fundamental constants, including the mass of the proton, the mass of the electron, the electric charge of subatomic particles, and the magnitudes of the fundamental forces of nature. If numerous figures were marginally altered, we would not be present. In other terms, one could modify the basic principles and physics would remain operational. However, the ramifications of these laws manifesting in the universe would exclude carbon-based life forms, such as ourselves. Atoms are bound by a robust nuclear force which operates over a limited range and functions as a binding agent, and a weak nuclear force which facilitates radioactive decay. Should the strong force be marginally more potent, atomic reactions would occur with such efficiency that stars would rapidly convert nearly all hydrogen in the universe into helium and subsequently into heavier elements, up to iron. Without hydrogen, water cannot exist. If the force were slightly diminished, the electrical repulsion among protons would prevent the formation of complex nuclei, thereby inhibiting the creation of carbon. If the weak force were slightly stronger, neutrons would decay rapidly enough to prevent the formation of heavy elements, causing nuclei to disintegrate. If it were somewhat weaker, an abundance of neutrons would exist, resulting in the conversion of all hydrogen into helium, and subsequently into heavier elements, leaving none available to form water. We are not discussing any substantial alterations. A bit in this context refers to 5 or 10%. There is additional information. The electromagnetic force regulates atomic interactions and elucidates the phenomenon of light. Should this force be marginally stronger, atoms would exhibit selfish behavior by refusing to share electrons, rendering chemical reactions impossible. Were it slightly weaker, atoms would fail to retain their electrons, resulting in a universe characterized by a dispersion of free particles, rendering chemistry impossible. Without chemistry, life would not exist. Our task is not yet complete. Gravity is the weakest force in nature. However, it is arguably the most significant, as it influences everything from the formation of planets to the expansion of the universe. Increased gravity would lead to the formation of larger stars, which would combust rapidly and exhibit instability. this scenario is unlikely to favor the existence of life on planets orbiting such stars. Weaker gravity is detrimental, as stars would fail to attain sufficient mass to undergo explosive death. Supernovae are essential for the synthesis of certain trace elements necessary for life and for the distribution of carbon and other heavy elements into areas conducive to the formation of new stars and planets. Cosmology offers additional enigmas. Throughout a significant portion of its history, the universal expansion decelerated as a result of the gravitational effects of dark matter. However, several billion years ago, we transitioned into a phase of acceleration as dark energy supplanted the comparatively weaker gravitational influence of the widely dispersed matter. The universe's history since the quantities of dark matter and dark energy influence the Big Bang. The commonplace particles constituting you, me, and our known world are negligible in their impact on the expansion. A universe with significantly less matter would have expanded more swiftly in its initial phase, so rapidly that gravity would not have had the opportunity to exert its influence before everything transformed into a cold, diffuse gas. In the absence of star and galaxy formation, life will not exist. A universe containing significantly more matter would have attained a maximum size and subsequently collapsed rapidly due to gravitational forces. Given our belief that biological evolution necessitates an extensive duration, potentially 1 billion years, a nascent universe such as this would still be regarded as a premature emergence. Similarly, if dark energy were significantly more potent, the universe would have disintegrated before life emerged. Currently, dark energy will induce galaxies to disperse at an accelerating velocity. This undermines the concept of intergalactic communication or a universal consciousness, as galaxies will ultimately recede faster than light can traverse the intervening distance. The physicist Freeman Dyson referred to this as a Carroll universe, named after Lewis Carroll, because it requires all the effort you can exert merely to remain stationary. Is existence unpredictable? The unique characteristics of our universe give rise to the anthropic principle. The anthropic principle is not a singular notion. It comprises a network of concepts and logical arguments, generating considerable controversy and confusion within the scientific community. In its most basic form, anthropic reasoning is a tautology. We can only perceive a universe that permits our existence. The most robust assertion posits that the universe must be configured in such a manner that intelligent observers can exist. Which option is it? We may acknowledge, indeed, the universe is ancient and vast, stars have synthesized carbon, and chemistry is feasible. If these assertions were false, our existence would be improbable. Alternatively, we may be astonished by the remarkable serendipity that resulted in our existence. When Nick Bostrom speaks, the most outrageous concepts appear rational, even self-evident. Bostrom is a contemporary philosopher who has extensively explored the anthropic principle, the Doomsday argument, and other arcane topics. He directs a new institute at Oxford University, yet he possesses the subtle sing-song intonation and refined vowels characteristic of a native Swede. Bostrom has emphasized the necessity of moderating our astonishment when contemplating the characteristics of the universe. Observational self-selection imposes a significant limitation on both the nature of our observations and their validity. The fisherman employing a net with 1-inch openings should not be astonished to capture only fish exceeding 1 inch in size. The Queen of England should not be surprised to awaken each morning and realize that she is the Queen. We cannot merely reference our existence to explain the specific characteristics of the universe. By broadening our definition of life and intelligence, the fine-tuning above appears less stringent. Life may not require carbon or celestial bodies. Conversely, fine-tuning remains relevant. The laws of physics do not preclude the existence of an exotic universe that expands and contracts within a year, A universe characterized by such profound disorder that time lacks a definitive direction, or a universe populated by magnetic monopoles. However, they are almost certainly deceased. Concepts from the forefront of physics offer a framework for comprehending the universe we inhabit. The Big Bang commenced as a quantum fluctuation set against a backdrop of space-time foam that may have been generated. It may continue to develop numerous universes, each possessing unique characteristics. The concept of the multiverse evokes an infinite array of universes, separate from our own. Their characteristics differ so significantly that life may exist in only a small subset, diminishing the uniqueness of our universe. Initially, the multiverse presents a peculiar contradiction to the scientific preference for simplicity in solutions. Nonetheless, it aligns with inflationary cosmology, and there are potential avenues for future observational validation. Simultaneously, theorists are endeavoring to accomplish the objective that evaded Einstein: the unification of relativity and quantum physics into a theory of everything. Rather than conceptualizing subatomic particles as diminutive spheres, we ought to envision them as one-dimensional strings or two-dimensional membranes, brains. They traverse a known three-dimensional environment situated within a 10-dimensional framework. We remain unaware of the higher dimensional space, which may encompass numerous parallel universes with varying physical laws and differing dimensionalities. The exceedingly complex mathematics about this is referred to as M-theory. M-theory establishes a foundation for numerous shadow universes. There may exist 1,010 distinct physical states of the vacuum, each imbued with potential. Self-selection implies that we will encounter environments possessing characteristics similar to those we observe. The theory may elucidate the rationale behind the existence of three spatial dimensions. Life is improbable in two dimensions due to insufficient complexity. Consider the distinction between dominoes and Lego bricks. Visualizing gravity in 4 or more dimensions is challenging. However, mathematical calculations reveal that gravity diminishes so swiftly that stars are unable to retain planets, and the altered forces within atoms render them unstable. In M-theory, 10-dimensional space organizes into configurations comprising either 3 or 7 dimensions. E. Cummings once playfully stated, "Listen, there exists a remarkably splendid universe adjacent. Let us proceed. We have traversed a speculative branch so tenuous that it may not support our weight. To focus on the empirical science of astrobiology, let us disregard the hypothetical parallel universes and the myriad galaxies beyond our vicinity. Let us reconvene and structure the information, alongside the misconceptions, into a framework that pertains solely to our galaxy. This culminates in the Drake equation." The Drake equation. The young researcher approached the blackboard and hesitated briefly. The meeting lacked an agenda, and he sought to impose some structure on the discussion. Upon reflection, Frank Drake inscribed an equation on the board, unaware that it would subsequently be named after him and achieve iconic significance. In 1961, the conference room at the Green Bank Radio Observatory convened the pioneers of SETI. The youthful Carl Sagan was present. Biochemist Melvin Calvin was present. Shortly thereafter, he would discover that he had been awarded a Nobel Prize for his research on photosynthesis. Dolphin researcher John Lilly commemorated the group's solidarity by establishing the Order of the Dolphin and distributing membership insignia to its members. 2 years prior, MIT physicist Philip Morrison ignited enthusiasm by co-authoring a paper positing that we could potentially detect a radio signal transmitted to us from another location within our galaxy. 6 months later, Frank Drake endeavored to detect artificial signals from 2 proximate stars. It was a period of significant optimism and anticipation. The group was cognizant of the Fermi paradox. They recognize that the majority of the arguments culminated in epistemological impasses. Speculation cannot replace the active pursuit of evidence for extraterrestrial life. Morrison articulated in his article in Nature, Searching for Interstellar Communication, that while estimating the probability of success is challenging, the likelihood remains zero if no search is conducted. Analogously, one cannot win the lottery without participating in it. The Drake equation comprises a set of numerical variables that collectively yield n, the quantity of communicating civilizations in the galaxy at any given moment. We are compelled to examine a momentary glimpse of a persistent and dynamic universe. Thus, two elements pertain to time. The remaining aspects pertain to the enumeration of habitable planets. The initial factor is the raw material for communication, specifically the rate of star formation that results in stars with sufficient longevity to support biological life. 6 factors influence the probability of transmission, whether intentional or unintentional. 2 are astronomical: the proportion of stars possessing planets and the average number of habitable planets per star. The subsequent 2 factors are biological: the proportion of habitable planets that develop life and the proportion of those that sustain intelligent life. The final 2 factors are contingent upon culture or sociology: the proportion of civilizations capable of interstellar communication and the average duration of the communication technology's viability. Let us employ an analogy. Several years prior, you encountered a girl with red hair. Her demeanor, perhaps her spirited gait or the somewhat ostentatious manner in which she chewed gum, captivated you. As she pivoted to depart, she audibly snapped her gum for emphasis, and that singular sound elicited a lump in your throat. What is the probability that a red-haired girl in your hometown is currently chewing gum and potentially causing emotional distress to another individual? Commence by assessing the birth rate of red-haired girls in the town. Assume the city possesses a population of 100,000. The annual birth rate is approximately 1,000. We multiply that by the proportion of new births with red hair, 10% or 0.1. The proportion that are female, 0.5. The proportion of those that are vivacious, approximately 0.2. And the proportion who will mature to chew gum, possibly 0.1. The result of all this is approximately 1. The final factor is the phenomenon's duration in years. It is minuscule, perhaps 1/10,000th, as even enthusiastic gum chewers dedicate only 10 minutes daily to blowing bubbles. In the analogy, the multiplication of all the factors results in n equals 0.0001. The occurrence of a red-haired woman chewing gum is infrequent. It is improbable that you will witness it. You are solitary. Nevertheless, the global population is 6 billion, or 60,000 times greater than the town. Globally, it is likely that a red-haired woman is currently popping a bubble. Similar to the Drake equation, the factors encompass both tangible and quantifiable elements, such as a town's population, and sociological aspects, including the conditions that prompt an individual to chew gum. The Drake equation encompasses both time and space. Continuing with the human analogy, it seems improbable that anyone else possesses our interests. Nevertheless, in a nation of 300 million individuals and a global population of 6 billion, it is feasible. What is the probability that 2 individuals have whistled a specific melody? Quite satisfactory. What is the likelihood that they have whistled the identical melody simultaneously? Significantly lower, and it may never have occurred. The attendees at the Greenbank SETI conference diligently input values into Drake's equation. The stellar birth rate was accurately quantified at approximately 3 new sun-like stars annually. Their estimation of the product of the four factors ranges from 1/4 to 1/2, assuming a few habitable planets per star and that all fractions are nearly 1. They posited that planets are omnipresent and that life, intelligence, and technology are almost unavoidable given the existence of a habitable planet. This identified them as optimists, as there was no data at that time, nor is there any now to substantiate that assumption. Consequently, all factors except the final one approximate to 1, leading to a simplified version of the Drake equation. N equals L. Drake, a silver-haired senior researcher at the SETI Institute, has this on his license plate. This underscores a critical point. The likelihood of contact is fundamentally contingent upon the duration of transmission technology's viability. This does not inherently equate to the civilization's lifespan. It may extend significantly if a civilization constructs beacons that continue to transmit after its demise. In 1961, the Green Bank participants acknowledged the significant uncertainty in this figure and designated a range of 1,000 to 100 million years. They estimated a broad spectrum, ranging from 1,000 to 100 million intelligent communicable civilizations in the galaxy. Impressive. The lifetime utilized in the Drake equation is an average, as distinct civilizations may engage in communication for varying durations. Average income can obscure significant disparities. When 90% of the population earns $10,000 annually and 10% are millionaires, the average income is $109,000, which is undoubtedly deceptive for the majority who are subsisting on $10,000. In a similar vein, if 90% of civilizations possess radio communications for a century, while 10% maintain communication for 100 millennia, the average L is 10,090 years. For SETI optimists, this is an encouraging indication, as a lineage of enduring civilizations can significantly elevate the average. The researchers convened at Green Bank with a strong interest in executing the experiment and chose the Drake equation parameters at the upper limit of their potential range. If habitable planets are rare, and if intelligence and technology do not necessarily arise from the emergence of life, then n may be significantly lower than 10 to the power of 3 to 10 to the power of 8. Pessimists would cite the Fermi paradox as evidence that n equals 1. Among the billions of stars in the Milky Way, we are singular. Numerous galaxies exist beyond our own, and there is no justification for considering the Milky Way exceptional. Thus, it is considerably improbable that the entire universe is devoid of biological life. However, a universe with neighbors distanced by millions of light years is quite a solitary environment. The number of active civilizations in the galaxy directly influences the nature of interstellar communication. Assuming the existence of 108 civilizations, 1 in every 1,000 stars harbors one, with the average distance to the nearest civilization being 30 light years. We could transmit signals within a human lifetime and reach that destination in a few centuries using the next generation of interstellar spacecraft. If the lower limit of the range is accurate, then merely 1 in 100 million stars harbors a civilization. They would be distributed sparsely throughout the galaxy, with an average separation of 10,000 light years. Moreover, if civilization endures for merely 1,000 years, it will have vanished by the time we detect its signals and endeavor to respond. Space may be populated with expanding spheres that contain the runes and glyphs of long-extinct civilizations. Decoding it would render the information invaluable as we endeavor to evolve into a mature civilization. Science fiction frequently employs the notion that one can gain entry into the Galactic Club provided one endures the initiation rites, or Rush Week. Hold on a moment. Pessimists, individuals with a pessimistic outlook, isn't science fundamentally based on logic and empirical evidence? Nevertheless, in the absence of ample data, scientists are prone to conjecture. When scientists engage in speculation, their biases and emotions infiltrate their cognitive processes. The inclination towards anthropocentrism is considerable, but should be opposed whenever feasible. While we cannot escape the human condition, it is beneficial to distance ourselves from our thoughts and emotions, occasionally. The Drake equation is constrained as a tool due to its reliance on conjecture and its deficiency in predictive capability. In mathematics, when a collection of numbers possesses an error or uncertainty, the uncertainty in the product of those numbers is determined by the most substantial uncertainty. In other terms, 3.14159 multiplied by 5.5 multiplied by approximately 0.1 multiplied by a range from 10 to 1,000 times. G, I don't know, equals. I am uncertain. We can address this issue by simplifying the Drake equation to distinguish observation from speculation. We must also interrogate its underlying assumptions. Initially, we reformulate the Drake equation as n equals n star times fh times ft times p. The initial quantity is the stellar count within the galaxy, n star. This is multiplied by a factor representing the fraction of stars with habitable planets, multiplied by the average number of habitable planets per system. To ascertain the number of prospective pen pals, the subsequent factor is the product of three variables: the proportion of habitable planets harboring life, the proportion of those planets hosting intelligent species, and the proportion of those planets where the species advances technology for interstellar communication or travel. The final factor, termed persistence, P, represents the ratio of a civilization's duration of existence to the age of the universe. Our primary objective is to quantify the number of habitable planets within the Milky Way galaxy. Approximately 200 billion stars exist in our galaxy. The quantity remains indeterminate due to the challenges in identifying faint stars, such as white dwarfs and low-mass solar analogs. However, they are excluded from the estimate because of their exceedingly narrow habitable zones. We aim to determine the number of stars that form planets. The formation of planets is contingent upon the availability of heavy elements. Both solid material and gaseous components are necessary. The prevalence of extrasolar planets is at least 5% for solar-type stars, increases to 25 to 30% for stars with 3 times the solar abundance of heavy elements, and may diminish to a negligible fraction for stars with less than 1/3 of the solar heavy elements. The Sun possesses a characteristic abundance of heavy elements. Let us recognize a prime location within the disk of our galaxy. In the outer regions of the galactic disk, the rate of star formation is insufficient to produce a significant quantity of heavy elements, suggesting that stars in these remote suburbs are likely devoid of planets. Near the galactic center, numerous stars are forming to produce planet-building material. However, the elevated supernova rate may pose risks to evolutionary processes. This zone of favorable conditions progresses with cosmic time, radiating from the galactic center. The ring surrounds us and comprises 1/4 of the stars in the disk. This results in 25 billion. A specific range of stellar mass can be established by omitting excessively massive stars, which have lifespans shorter than 4 billion years, the duration required for advanced life to develop on Earth, and stars that are significantly less massive than the Sun, as their habitable zones are exceedingly limited. This is a prudent selection. It may require less time in other contexts. We have reduced the number to 5 billion, 3/4 of which are older than the Sun. Observe the magnificence of vast quantities. We have eliminated 195 billion stars, yet a substantial number remain. The subsequent step is to ascertain the proportion of these stars that possess terrestrial planets and the typical number of stars exhibiting this trait. We eliminate all gas giants, presuming that life cannot thrive under the elevated pressure at the depths of such substantial atmospheres. However, this may be erroneous. We must transcend direct observations as planet hunters are only now attaining the requisite sensitivity to detect super-Earths. It is a scientific conjecture. We observe 7% of Sun-like stars possessing gas giant planets. To extrapolate this to Earth-like planets, we could augment this by a factor of 2 to 15%, as the solar system comprises 4 terrestrial planets alongside Jupiter and Saturn. Simulations consistently indicate the presence of 2 to 4 terrestrial planets in a typical system. Excluding the 2/3 of stars that are binary or multiple, the proportion decreases to 5%. This may be overly cautious, as Frank Lin at the University of California, Santa Cruz, has demonstrated that planets can also form in a standard binary system. 2 stellar progenitors are better suited to support stable orbits than 1. Only the most uncommon close binaries would perturb their orbiting planets. We have identified 250 million terrestrial planets orbiting approximately 125 million stars. Let us designate this as the teetotaling, short back and sides, ultra-conservative assessment. By sheer coincidence, with minimal data, English philosopher Thomas Wright approximated 170 million worlds in 1750. Let us relax and consider a still feasible yet more optimistic estimate. The quantity of exoplanets increases swiftly at the threshold of current detection capabilities, suggesting that the observed proportion of 7% of Sun-like stars possessing 1 or more gas giant planets is likely a significant underestimation. Meticulous models indicate that we are observing merely the surface of the planet's population. The observations suggest that all such stars possess giant planets, contingent upon the availability of superior data. Moreover, the formation of terrestrial planets is more straightforward, as substantial gas accumulation is unnecessary, although some gas giants may expel their smaller counterparts from the system. Gravity influences minor planets more readily than it does larger ones. Therefore, we shall apply the factor of 2 observed in our solar system. This results in an estimation of 10 billion terrestrial planets orbiting 5 billion stars. Habitability. Astrobiologists unanimously agree that the essential prerequisites for life include organic or carbon-based compounds, liquid water, and a source of energy. In a solar system analogous to ours, if planets form with uniform probability up to 3 astronomical units, the liquid water zone, spanning from 0.9 to 1.2 astronomical units, constitutes 10% of the total range. Consequently, we estimate that there are 25 million habitable worlds in the galaxy. This figure represents a lower threshold, as we have exercised caution at every juncture by excluding binaries, disregarding the numerous dwarf stars, failing to consider the probable simplicity of forming terrestrial planets, overlooking moons of giant planets, and adhering to a stringent definition of the habitable zone. Let us take a moment to contemplate. 25 million potentially habitable worlds exist within our galaxy alone. That is the approximate estimate. What of the dreadlocks or the ponytail that extends to the lower back? We acknowledge the evidence indicating that the large moons, Europa, Callisto, and Ganymede, possess oceans, along with models proposing that approximately 12 additional sizable moons also contain subsurface oceans. The conventional habitable zone is inconsequential. Moons distant from their stars can sustain liquid water beneath a rocky or icy crust due to pressure, and heat may be produced through tidal forces or radioactive decay. We should also reintegrate the substantial population of long-lived, low-mass dwarf stars into the census. We achieve 2 orders of magnitude. Numerous billion potentially habitable celestial bodies exist within our galaxy. Do we presume that all these biological petri dishes can remain uncontaminated? Or do we believe that microscopic life has proliferated on many of them? We now tread upon increasingly fragile ice. The subsequent variable in the Drake equation is the proportion of habitable planets where life evolves to intelligence and technological capability. It is the product of three quantities, the first being the proportion of habitable planets on which life emerges. Evidence of past or present life on Mars or Europa would indicate that this fraction approaches 1, suggesting multiple independent origins of life within a single solar system. A supplementary, albeit less robust, argument arises from the swift emergence of life on Earth and the adaptability of extremophiles. It appears that life was nearly unavoidable. 13. Assume we accept this argument. If we were not so preoccupied with companionship, we could conclude at this point, regardless of whether we assume that solely Earth-like water worlds develop life or that 1% of the significantly greater quantity of water-bearing moons become biological. The conclusion remains unchanged. Envision countless millions of habitable planets within our galaxy. Consider the myriad biological experiments, each characterized by distinct physical environments and biospheres as unique as fingerprints. Incorporating all galaxies beyond the Milky Way suggests an astonishing million-trillion iterations of life in the universe. The subsequent topic is the proportion of instances in which a planet possessing biological life evolves intelligent beings. How can we define intelligence without resorting to self-reference? Focusing on our cognitive modalities risks producing a definition that may stem from contingent evolution and Earth's specific environmental conditions. It is essential to differentiate between cognition and conduct. A multitude of animals on Earth exhibit intricate behaviors for survival and reproduction. Their brains function as instruments that analyze environmental information and respond accordingly. However, complex behavior can occur without cognition. Intelligence can be defined by two additional attributes: the capacity for self-reflection on experiences and the faculty of abstraction. Reflection facilitates learning that transcends operant conditioning. Abstraction enables the handling of concepts that are not embodied by tangible entities. Counting encompasses both reflection, I observe two dogs, and abstraction, I perceive two entities, which could potentially be cats. These attributes facilitate the creativity that we often believe is solely the domain of humans. What is the evolution of human intelligence? We gain significant insights from our categorization within the web of life. We belong to the domain eukarya, characterized by large cells with nuclei, and our evolution was influenced by the accumulation of oxygen in the atmosphere billions of years ago. We belong to the animal kingdom, characterized by movement, sexual reproduction, and a variety of specialized cell types. In the evolutionary hierarchy, the four additional kingdoms, plants, fungi, bacteria, and protists, effectively colonize the planet without the advantage of a centralized intelligence system. We are chordates, distinguished by internal skeletons that safeguard our central nervous system. Approximately 700 million years ago, the antecedents of contemporary brain cells emerged. Amphibians that inhabit aquatic environments transitioned to terrestrial life and evolved into reptiles around 350 million years ago. By the late Cretaceous, around 65 million years ago, all principal vertebrate taxa, fish, amphibians, birds, reptiles, and mammals had evolved distinctly structured brains. We are mammals characterized by fur and endothermic physiology. The shrew-like Hadrocodium wui traversed a dinosaur-dominated environment 200 million years ago, weighing less than a dime. Nonetheless, its brain was exceptionally pronounced relative to its body. Large oak trees originate from small acorns. Dinosaurs outcompeted mammals during the diversification of life that ensued after the Permian-Triassic extinction event 250 million years ago. It was only after the subsequent mass extinction 65 million years ago that mammals exceeded the size of a squirrel. Early primates were characterized by a heightened dependence on vision over olfaction, prehensile digits, and intricate social structures. The emergence of acute, stereoscopic vision likely stimulated the evolution of larger brains. In contemporary humans, visual processing constitutes roughly 10% of the brain's capacity. The fossil record is incomplete, however, it suggests that the hominid lineage diverged from apes approximately 6 to 8 million years ago, as our early ancestors began to adopt bipedal locomotion and evolved from forest-dwelling inhabitants to foraging nomads in the African grasslands. Our brains progressively expanded to surpass those of all other ape species. DNA analysis corroborates the fossil evidence that all 6 billion inhabitants of this planet are descended from a limited group of geographically isolated individuals who resided in Africa around 200,000 years ago. Gazing into the eyes of a great ape reveals the self-awareness of beings that share 99% of our DNA. It is a mere historical accident that we do not coexist with Neanderthals, whose cranial capacity was marginally greater than ours and who became extinct less than 25,000 years ago. A brief moment in evolutionary history. Is intelligence an unavoidable consequence of natural selection? The development spanned nearly 4 billion years and occurred in only a few species among the hundreds of millions that have existed, the majority of which are now extinct. Intellectual capacity is not a prerequisite for evolutionary success. They provide a selective advantage by processing vast quantities of sensory information and facilitating cognition that results in adaptive survival strategies. 15. Conversely, substantial brains require upkeep. They necessitate a high-protein diet and meticulous temperature regulation. Approximately 25% of our metabolism is allocated to cerebral function, representing a significant investment. The vulnerability of large organisms suggests that the criteria for a habitable zone should be more rigorously delineated to facilitate the evolution of intelligence, as climatic extremes may prove lethal. This argument is paradoxical, as significant glaciation events may have encouraged the emergence of complex animal life. The necessity for temperature stability is less stringent for marine organisms, as water serves as a thermal reservoir, moderating temperature fluctuations. We unequivocally acknowledge that humans are unparalleled. No other species has conceived art or mathematics. No other species has developed machines to enhance its sensory perception and execute its commands. No species has altered the planet as profoundly since stromatolites and other early photosynthetic organisms. Psychic immaturity leads to the infliction of pain and chaos, yet the underlying potential is undeniable. In astrobiology, it is prudent to adopt a more expansive perspective. If our intelligence dictates the definition, we will only acknowledge beings resembling us as intelligent. Evolution persists, suggesting that intelligence on Earth may not be exclusively confined to humanity. Let us establish the standard of self-reflection and abstraction. Evidence suggests that we share a comparable level of intelligence with dolphins and orcas, whose most recent common ancestor with primates existed 85 million years ago. They possess brain-to-body mass ratios akin to those of humans and superior to those of other mammals. Particular avian species exhibit reflective behavior. Furthermore, let us avoid a mammal-centric perspective. Cephalopods possess substantial brains and remarkable abilities for learnt behavior, despite their more distant evolutionary relationship to humans. You are positioned on a desolate Ordovician coastline. A panorama of desolate rocks extends behind you into the horizon. The horizon is unobstructed by trees, and there are no plants or animals present. Your lungs exert considerable effort inhaling air containing 25% less oxygen than usual. The Earth rotates more rapidly on its axis, resulting in a day lasting merely 21 hours. The moon appears nearer in the sky. Water gently caresses your feet. Suddenly, the surface is disrupted by a colossal horn measuring 30 feet in length. Its polished shell is variegated with muted red and white, culminating in a cluster of tentacles. Another splash, and it has vanished. This unusual tableau depicts Earth 470 million years ago. For 70 million years, since the Cambrian explosion, a notable evolutionary struggle has transpired in the oceans. The chordates, our remote ancestors, are not prominently involved in this conflict. The initial victors were predatory arthropods. Following significant climate change and a mass extinction, the small-shelled mollusks capitalized on the opportunity. Beginning as rudimentary chambered shells measuring a few millimeters, within 50 million years, they had evolved and diversified into organisms such as Camaracaras, which barely surfaced. During the Ordovician period, colossal cephalopods dominated the oceans. Cephalopods represent some of the most successful life forms on Earth. The nautilus has persisted with minimal alterations for 400 million years, enduring multiple mass extinctions by foraging in the dim depths of coral reef slopes. Their relatives, cuttlefish, squid, and especially the octopus, exhibit some of the most complex behaviors in the animal kingdom. They are shapeshifters, equally peculiar as Odo from Star Trek. Roger Hanlon became fascinated with cephalopods during his junior year of college when an octopus on the Panamanian Reef surprised him. Currently a senior researcher at the Woods Hole Marine Biological Laboratory, he has been investigating the octopus in its natural habitat for over 30 years. His most exceptional dives occur in the Caribbean, and he chuckles when asked whether he still encounters surprises after thousands of hours of observation, asserting that he has barely begun to catalog their intricate lives. Hanlon refrains from addressing the octopus's intelligence, claiming that it is simplistic to impose our cognitive frameworks onto these unique beings. He favors observing and interpreting his observations. Despite authoring a book on cephalopod behavior, Hanlon adheres to the principle of esteemed zoologist Louis Agassiz: study nature, not books. Vertebrates, including humans, utilize a command and control architecture wherein the brain functions as a centralized processing unit to receive sensory input and regulate limb movement. In contrast, an octopus possesses a centralized brain and an extensively distributed neural network. It can be conceptualized as a mind integrated with a body. Commence with locomotion. An octopus possesses intelligence within its appendages. Each arm possesses a complex nervous system comprising 50 million neurons, and each exhibits an extensive range of continuous motion. In contrast, our rudimentary configuration of knees and ankles, as well as elbows and wrists, appears rather primitive. The arm possesses an intrinsic motor program. The octopus is distanced from humans, lacking centralized control. The brain, within the tree of life, imparts an initiation directive to us. Subsequently, binocular vision, an enlarged brain, and sophisticated intelligent appendages dominate. The octopus eye is as sophisticated as the human eye, despite its differing design. The method for assessing octopus eyes remains unknown. However, the octopus maintains precise alignment of its eyes, irrespective of its body orientation. It can detect the polarization of light, aiding in the perception of transparent prey, including prawns and fish. The eye and brain work together to accomplish advanced pattern recognition, which is essential in intricate environments like coral reefs. An octopus possesses chemoreceptors in its suckers, enabling it to taste objects it contacts and promptly discard unsuitable food items. As a predator, it is unmatched, rapid, robust, driven by a jet of water, and equipped with suckers, a beak, ejected and directed ink, and venomous saliva. The giant octopus can reach a weight of 100 pounds, yet certain legends surrounding them are exaggerated. When encountering humans, they exhibit curiosity and gentleness. The remarkable characteristic of an octopus may be its skin, a direct extension of the brain utilized for camouflage and communication. Translucent sacs, known as chromatophores, contain pigments of diverse hues: yellow, orange, red, brown, and black. When the muscles connected to each sac contract, it expands, revealing its color. Cells situated beneath the chromatophores function as iridescent reflectors of various colors, facilitating optical interactions of remarkable complexity and beauty. The skin of an octopus can rapidly change in texture, seamlessly imitating the smoothness of coral, a sponge, or the corroded remains of a submerged vessel. Significant processing power is required for 20 million skin pixels to choose from a palette of hundreds of thousands of colors in less than 1 second. Comparing an octopus to a chameleon is derogatory. Numerous behaviors are ingenious. An octopus can expel a cloud of ink in its form, disorienting a predator sufficiently to facilitate its escape. They can detach an arm as a decoy. The severed arm will persist in changing colors and moving, serving as an effective distraction. Octopuses retain intricate visual signals to traverse the perilous terrain of the coral reef, a three-dimensional environment that can confuse even seasoned divers like Hanlon. In confinement, octopuses exhibit remarkable escape abilities, capable of traversing openings no larger than their ocular diameter. There exists contentious evidence suggesting that octopuses can acquire knowledge through the observation of others' behavior. Evolution is not static. Cephalopods possess the capacity to acquire novel abilities. Humans may fall victim to microbes or their arrogance. We can envision a future not far off when the progeny of the octopus, ever inquisitive, make their initial cautious forays onto land. The emergence of technology elsewhere in the universe is even more unpredictable than the challenges associated with forecasting self-aware and abstract intelligence. Technology is, in one regard, a natural outcome of evolution. Millions of years ago, Earth's organisms developed the ability to fly, use sonar, employ fiber optics, sense magnetic and electric fields, detect seismic and pressure changes, and utilize holography. Humans have existed for hundreds of thousands of years, yet we have only achieved that list in the past century. In technological transitions, tools are essential. However, their use is not exclusive to humans, as apes, birds, otters, elephants, and dolphins also employ tools. They utilize sponges to shield their noses while foraging on the seafloor, a technique transmitted through familial lines. To imply that humanity's progression towards modern technology is inevitable would be a distortion of history. Neanderthals utilized stone tools for over 100,000 years without progressing to more advanced implements. Early milestones in human technology were likely serendipitous, including the mastery of fire, the emergence of agriculture derived from natural mutations of wild rye with larger seeds that descended rather than dispersed by wind, and the creation of bronze, which catalyzed the first significant civilizations 6 millennia ago. 17. If the concern pertains to communication with extraterrestrial intelligence, it is evident that we are discussing technology that surpasses that utilized for adaptation and survival. In addition to intelligence, let us incorporate 2 attributes. One pertains to the capacity to manipulate and govern matter and energy at will. The other refers to the propensity to employ technology for space exploration. Technology is not an inevitability. Octopuses, dolphins, and particular avian species may exhibit comparable cognitive capacities, yet they cannot direct telescopes towards the cosmos and contemplate their existence within the universe. After evaluating the aspects of intelligence and technology, how do we assess the subsequent variable in the Drake equation? Possessing the intelligence and resources to explore the universe does not guarantee that the outcome is inevitable and the probability approaches 1. Such reasoning is flawed. For each planet hosting a civilization akin to ours, there may exist millions of planets where life did not progress to advanced intelligence. In these millions, cognitive development did not result in technological advancement, or millions where technology is not employed for space exploration and communication. Consequently, we will defer this factor while we investigate the other essential criterion for companionship: persistence. Timing is paramount. The final variable in the Drake equation pertains to temporal considerations. The emergence and extinction of species dictate that the continuity of civilization and technology influences the probability of encountering others or their remaining machines for communication. The Milky Way's age and the Sun's lifespan are each approximately 10 billion years. Thus, we must assess the duration of a technological civilization as a proportion of this extensive time frame. Contemplate an irrefutable truth. Our ability to explore space is remarkably recent on a cosmic timescale, less than a century or approximately 10 to the power of 8 of the galaxy's age. The pessimist may contend that we are nearing self-destruction due to nuclear weapons. We could consider the standard duration of our principal civilizations, 1,000 years, as a minimum threshold, resulting in p equals 10 to the negative 7th power. Envision possessing a Christmas tree for 2 weeks. You have purchased lights, yet each illuminates for merely 1 second throughout the entire fortnight. Despite the presence of numerous lights, the likelihood of 2 being illuminated concurrently is exceedingly low. This mode of communication would render extraterrestrials extraordinarily isolated. The upper limit on persistence is mere conjecture. If we or other civilizations can protect ourselves from the mechanisms of natural selection, we may endure significantly longer. Longevity transitions into immortality as the quantity of genuinely advanced civilizations in the galaxy progressively rises over time. While immortality is intriguing, a more sobering consideration is the Doomsday argument. In his office at Princeton, J. Richard Gott III examines the extinction of humanity with both depth and engagement. He articulates with a melodious Kentucky accent and adorns himself in elegant pastel hues that stand out in the monotonous academic environment. In 1969, Gott, as a student, visited the Berlin Wall and, after having seen other landmarks such as Stonehenge, contemplated its longevity. Gott posited that if he were to visit the wall at a random moment during its existence, there was a 75% probability that he was observing it after the initial quarter of its lifespan. He observed it after it had been displayed for 8 years, leading him to anticipate its absence post-1993, 1961, plus 3 times 8. It collapsed in 1989. For humans, Gott transitioned to the standard in physics of quantifying estimates with 95% confidence, yet the reasoning remains unchanged. It is identifiable as a manifestation of the Copernican principle. In the absence of any particular timing, there exists a 95% likelihood of observing an entity within the central 95% of its lifespan. This indicates that there is a 95% probability of the object enduring for a duration ranging from 1/39th to 39 times its present age. For humans, this corresponds to a span of 5,100,000 to 7.8 million years. According to this rationale, our existence is not eternal. Philosophers have both endorsed and criticized the Doomsday argument. John Leslie, professor emeritus at the University of Guelph, invites us to contemplate 2 urns filled with numbered balls. One urn contains 10 numbered balls, while the other includes 100 million. But their identities are unknown to you. Assume you select a ball inscribed with the numeral 7. It would likely be selected from the urn containing balls numbered 1 to 10, rather than from the urn containing balls numbered 1 to 100 million. Envision the urns as representations of potential human races, while the balls symbolize individuals arranged in order of birth. If your rank is 70 billion among all humans who have ever existed, it is more probable that the total population will be 100 billion rather than several trillions. This reasoning suggests that humanity is closer to its conclusion than its inception. The Doomsday argument posits that intelligent civilizations are ephemeral and solitary within the context of cosmic time. Irrespective of the duration of civilizations, we can derive two conclusions. If we are not solitary, it is improbable that we are the pioneers. Sun-like stars have existed with sufficient heavy elements to form planets for 12 billion years. That duration is threefold greater than the period during which life has existed on Earth. Unless 4 billion years is an exceptionally brief duration for the emergence of civilizations, extraterrestrial beings may have attained our level of development billions of years before us. This leads to the second conclusion. Given that we have only recently developed the ability for space travel and communication, any civilization we encounter is likely to be significantly more advanced than ourselves. Arthur C. Clarke stated, "Any sufficiently advanced civilization is indistinguishable from magic." In 1959, physicist Richard Feynman delivered a lecture entitled, "There is Plenty of Room at the Bottom," in which he forecasted the emergence of nanotechnology, the capacity to manipulate devices and fabricate structures at the atomic level. Approximately concurrently, DNA co-discoverer James Watson stated, "Life is digital information. What if we emancipated ourselves from the structure of a singular biological paradigm? What impact could that have on the prevalence and persistence of intelligent life?" Initially, contemporary organisms exemplify the pinnacle of information compression. Each human red blood cell possesses a genome containing a volume of genetic information equivalent to that of a compact disc, encapsulated within a structure measuring 1/100th of a millimeter in diameter. Nevertheless, if life could function without cellular infrastructure, biochemical processes could be more concentrated and operate with greater efficiency. We regard nucleated cells as the most sophisticated and successful life forms on Earth. Nonetheless, intriguing subcellular entities exist that possess essential functions, although biologists fervently dispute their status as alive. They exist in parasitic and symbiotic associations with their hosts. Certain entities induce diseases, whereas others confer advantages. They lack cell walls, most do not metabolize, and some possess no genetic code. Take, for instance, Spiegelman's monster. In 1997, Sol Spiegelman was conducting research on strands of viral RNA in the laboratory. Despite the absence of cells, the RNA fragments readily replicated. As they proceeded, strands initially measuring 4,500 nucleotide bases in length began to diminish, shedding unnecessary segments of the genome. Shorter strands replicated more swiftly, culminating in a diminutive genome of 50 base pairs that outperformed all others in reproduction. Previous experiments conducted by Manfred Eigen demonstrated that RNA strands, comparable in size to Spiegelman's monster, spontaneously formed from a mixture of single nucleotides. Conventional biological wisdom posits that the survival of the smallest presents a challenge for evolution, as it obstructs the development of larger and more complex organisms. Small organisms possess a restricted capacity for genetic evolution, hindering significant evolutionary advancement. Conventional wisdom may be erroneous or, at the very least, myopic, as it relies on the just-so story we narrate regarding life on Earth. The rapidity and efficacy of diminutive replicators may represent the predominant mechanism by which biological development occurs. Richard Dawkins encapsulates the fundamental principle of biology in a slogan he deems suitable for a t-shirt: "Life arises from the non-random survival of randomly varying replicators." Complexity may emerge from networks of diminutive molecular units, and if this occurs rapidly, the necessity for several billion-year-old stars can be obviated. Intelligence may emerge in networks of diminutive biological entities. as illustrated in the introductory vignette, rather than in centralized organs like brains. This intelligence may exhibit greater adaptability and resilience than our own, which relies on survival and the management of delicate bodies. The typical distance between civilizations spans hundreds of light years. However, civilizations endure for millions of years, rendering this distance relatively insignificant. Virtually every individual we encounter possesses advancements that surpass ours by millions of years. The extensive duration of civilizations, spanning billions of years, may amass the galaxy's wisdom and establish a network of beacons, enabling newcomers like us to locate the nearest probe for knowledge acquisition. Resilient civilizations are not confined to our immediate vicinity. Knowledge may traverse the galaxies. Philip Morrison stated, "SETI is the archaeology of the future." Speculation is entertaining. However, in the absence of evidence, it resembles a dog pursuing its tail. Observations may never resolve the debate regarding the existence of extraterrestrials, yet they cannot be resolved in their absence. We have conversed throughout the night and listened attentively. Through the act of communication, we transcend the inquiry. Where are they? To inquire, who are they? Kent Cullors envisions himself at the control console of the Allen Telescope Array. The year is 2015. Paul Allen, co-founder of Microsoft, financed the facility. It comprises 350 radio dishes, distributed throughout a northern California valley. The processors operate concurrently, processing gigabytes of data per second from the radio signals collected from space. Radio waves effortlessly traverse the gas and dust of interstellar space, and the Allen Array is capable of observing across the galaxy. In addition to substantial raw processing power, patience is essential. Cullors is a patient individual. Before his recent retirement, he was employed at SETI for 3 decades. This glimpse into the imminent future is not an exaggeration for Cullors. In his youth, Cullors' father depicted the planets with such vividness that Cullors could envision himself present among them. In 1980, he was motivated by a report on the unfunded Project Cyclops, which had the potential to identify a counterpart to our technological civilization among the nearest million stars. Cullors envisions the potential methods of communication employed by extraterrestrial intelligence, despite being blind since birth. SETI researchers have endured a tumultuous journey of heightened expectations and disillusionment for decades. At the dawn of the 20th century, the pioneers of emerging radio technology recognized its potential as a means of communication with celestial bodies. The brilliant and eccentric inventor Nikola Tesla pioneered alternating current, AC power generation, which faced opposition from Thomas Edison, who advocated for his direct current DC system. In the process of transmitting power wirelessly, he asserted that his transmitter was receiving signals from extraterrestrial sources. 2 decades later, Guglielmo Marconi believed he had identified radio waves originating from space. Both men likely perceived distant lightning as whistlers. The radio frequencies they operated at were insufficiently high to be transmitted through the Earth's atmosphere from an extraterrestrial origin. In 1960, the year preceding the formulation of his eponymous equation, Frank Drake directed an 85-foot radio dish from the National Radio Astronomy Observatory in Green Bank towards the sun-like stars Epsilon Eridani and Tau Ceti. He adjusted the dial of his receiver to 1,420 megahertz, the frequency corresponding to a fundamental transition of hydrogen, the most prevalent element, and listened for several weeks. He perceived solely radio static. In a moment of whimsy, Drake designated his search as Project Ozma, after a character from the children's literature by L. Frank Baum, which included peculiar and exotic characters from distant lands. In 1977, an investigation at the Ohio State University Radio Observatory produced a solitary yet potent radio signal that seemed artificial. The signal strength was documented. Subsequently, upon observing its intensity, the astronomer on duty remarked, "Wow," on the printout. The signal did not recur. SETI has consistently maintained a tenuous relationship with popular culture, characterized by a prevalent belief in extraterrestrial life. The subject is often unjustly tainted by a hint of disrepute. Following the Green Bank meeting that initiated the Drake equation, dolphin researcher John Lilly transcended conventional boundaries, engaging in LSD experimentation and documenting dialogues with extraterrestrial beings. In 1978, the notoriously anti-intellectual Senator William Proxmire awarded SETI the Golden Fleece Award, denouncing it as a flagrant misuse of taxpayer funds. Astronomers suggested the senator for membership in the Flat Earth Society. SETI's rapport with Congress has been fraught. In 1993, Senator Richard Bryan of Nevada eliminated SETI funding from NASA's budget, asserting that after years of exploration, they have yet to capture a single little green fellow. This posturing was particularly ironic, considering he also advocated for renaming Nevada Highway 375, which runs near the infamous Area 51, as the E.T. Highway. Kent Cullors has encountered the usual criticisms of SETI, that it presupposes too much regarding the essence of intelligence, that it is predicated on specific concepts of language or perception, and that it is irredeemably anthropocentric. The initial artificial signal could be a numerical sequence, a collection of prime numbers or binary pulses that characterize a Turing machine, the universal computer. Cullors acknowledges that the probability of success is slim, and he understands that it cannot be accurately quantified logistically. He is committed to the long term, having already surmounted significant personal challenges. During his college years, the majority of physics texts had not been translated into Braille. "I had to pose numerous inquiries and solicit explanations from my classmates," he states. He endeavors to eliminate all assumptions and focus on the challenging issue of detecting signals amidst cosmic noise. Jill Tarter remains resolute after decades of the Great Silence. She observes that SETI has enhanced its capabilities by 14 orders of magnitude since Project Ozma. Instead of fixating on past failures, she believes the exploration is merely commencing to become intriguing. Tarter is an individual who is wholly dedicated to maintaining the trajectory. She has had to counter numerous challenges related to gender disparity in science. During high school, she was directed towards home economics, and she was the sole female in her cohort of the engineering physics program at Cornell. She inadvertently became involved in SETI as a graduate student at Berkeley, during an era when the initiative still elicited derision from fellow scientists. Ellie Arroway, the protagonist in the film Contact, was partially inspired by Tarter, who assisted Jodie Foster in preparing for the role. According to Anne Druyan, a producer on Contact and co-writer of the TV series Cosmos with her late husband, Carl Sagan, Ellie Arroway was a composite character. Hypatia served as the inspiration for the character. Ellie alludes to Eleanor Roosevelt, while Arroway is an anglicized rendition of Voltaire's actual name. Jill Tarter and Carolyn Porco were influential contemporary women scientists who defined the role. "I belong to the inaugural generation of humans capable of exploring the age-old question, are we alone? Question," states Tarter, "for millennia, humans have sought the beliefs of priests and philosophers." Tarter holds a distinguished chair at the SETI Institute, named in tribute to another SETI pioneer, Bernard Oliver, who edited the Project Cyclops report that initially captivated her imagination. The SETI Institute was established in 1984 to augment the funding available from NASA for researchers. The research has garnered corporate and philanthropic backing, with significant contributions from Paul Allen and Steven Spielberg. Fundraising persists for what could be a multi-generational investigation. Notwithstanding challenges with federal funding, SETI has generated the largest and most widespread research community in any scientific discipline. The SETI League is an informal consortium of amateur radio astronomers who generally utilize discarded satellite dishes to detect artificial signals. Their ambitious objective is to deliver 5,000 dishes globally, ensuring uninterrupted coverage of the sky. Simultaneously, individuals possessing a personal computer and a modicum of patience can engage in this idealistic endeavor. SETI at Home was the forerunner of a new generation of initiatives aimed at utilizing the dormant processing capacity of personal computers for scientific inquiry. A freeware application can download data segments from the internet and analyze them as a background process, relaying the findings to a central server. You may also contribute to climate change research, investigate gravitational waves, engage in biomedical studies, or aid in the design of a particle accelerator. SETI was the inaugural attractive application for distributed computing and remains the most extensive to this day. SETI at Home boasts over 6 million participants across 255 countries, including 60 from the diminutive island nation of Vanuatu. Thus, do not be the last individual to join the initiative. Since 1999, this supercomputer has utilized 3 million years of processing time, executing 35 trillion calculations per second. Radio SETI optimistically searches for a signal in a cosmic haystack. Astronomers examine the tranquil regions of the radio spectrum for signals that are too narrow to result from any recognized astrophysical phenomenon. Repetitive pulses, or those exhibiting a discernible pattern, are potential indicators of extraterrestrial messages. The strategy integrates superficial scans of the entire sky with in-depth observations of specific stellar targets. Project Phoenix operated from 1995 to 2004, focusing on 800 stars within a range of 240 light-years. Each star was examined across 2 billion narrow channels, ranging from 1,000 to 3,000 megahertz, accumulating a total of 11,000 hours of observation. The most formidable instrument in the search was the 300-meter Arecibo dish, the largest in the world. Frank Drake emphasizes that, were its aluminum panel surface not perforated with a grid of holes to reduce weight, it could contain all the beer consumed in the United States. The Allen Telescope Array is intended to consist of approximately 356-meter radio dishes, situated in a lava-strewn valley near Hat Creek, north of San Francisco. The array is designed to enhance computer performance and signal processing, with a goal of 350 dishes in total. The project will examine 1 million stars within a radius of 1,000 light-years, analyzing 12 billion channels ranging from 500 to 11,000 megahertz for each star. By integrating sensitivity, bandwidth, and target quantity, it will yield an additional billion-fold increase over the cumulative results of all prior searches. Tartar is enthusiastic because a substantial portion of the cosmic haystack will be examined. However, the Allen Telescope Array lacks complete funding, and Tartar acknowledges that securing financial support can be challenging when individuals perceive a connection to a billionaire from Microsoft. Motivated by Charles Townes, the inventor of the laser, SETI has broadened its search to include optical wavelengths. Utilizing our advanced pulsed lasers and a substantial telescope, we can produce a terawatt of power, which constitutes 25% of the nation's energy consumption. To prevent a widespread brownout, it is executed for merely 1/billionth of a second and transmitted into space. If extraterrestrials were engaging in similar activities on a planet orbiting a nearby star, we could identify the pulses for brief moments when they surpass the intense luminosity of the star. A laser 1 billion times more potent could be observed across the galaxy. The medium constitutes the message. Due to the inability to predict the thoughts or language of extraterrestrial intelligence, SETI researchers seek signals that lack a natural astrophysical explanation. However, a few phenomena that disturb the night, such as quasars and gamma-ray bursts, were never anticipated, making it difficult to discern what is natural and what is extraterrestrial. Following the detection of metronomic signals from the initial pulsars, researcher Jocelyn Bell from Cambridge University humorously designated them LGM1, LGM2, and so on, referencing little green men. The prevailing approach involves seeking radio pulses with excessively narrow frequency, 1 Hz, or optical pulses that are exceedingly rapid, 1 nanosecond, to be produced without technological intervention. Jill Tarter and Kent Cullers recognize that determining whether a signal is artificial and non-random will be significantly simpler than deciphering its meaning. Given that we cannot communicate with Earth's animals, which share 99% of our DNA, how probable is it that we will comprehend extraterrestrial beings of indeterminate function and morphology? Our efforts to communicate may appear antiquated. The Arecibo message, featuring stick figure and radio telescope silhouettes, resembles petroglyphs transmitted into space. The recordings affixed to the Voyager spacecraft, launched in 1977, are in an analog LP format that is already obsolete on Earth. The cover provides instructions on how to play and appreciate the sounds, presuming the recipient possesses auditory capability, an atmosphere, linguistic proficiency, and the willingness to utilize retro technology. We have also been communicating unintentionally. A sphere of radio waves transmitting our early television broadcasts has traversed at the speed of light, passing by 10,000 stars to date, with hundreds more anticipated to be encountered annually. Extraterrestrials either anticipate our forthcoming sitcoms and reality shows or have dismissed us as a viable civilization. The timing issue is significant in SETI. Reflecting on our progress, predicting the future appears nearly impossible. To recognize the novelty of our technology, contemplate a civilization that advanced beyond our current level of development before the formation of Earth, and has intermittently monitored us since that time. Let us condense the history of the Earth into 24 hours. Life emerges after several hours and remains diminutive and unremarkable until 1 hour before midnight. Modern humans emerge just before the stroke of midnight. SETI posits a significant correlation among intelligence, technology, and interstellar communication. Cetaceans and cephalopods demonstrate that intelligence does not necessarily correlate with technology, suggesting that the utilization of technology for interstellar communication may be a distinct cultural characteristic. SETI may only examine a minuscule portion of the intelligent species that exist. What is notable is our necessity to communicate, a desire that nearly ascends to a yearning. The universe may be teeming with microbial organisms. The inconclusiveness of the Great Silence suggests the potential existence of numerous intelligent beings in the universe. The temporal argument suggests that if they exist, they are significantly more advanced than humanity. Let us trace the logical sequence one final step. Our hand grasps a bottle inscribed with a straightforward directive: consume me. Hans Moravec has envisioned robots throughout his entire life. For the last 30 years, he has been actualizing dreams in his laboratory through a succession of progressively advanced robots. In the 1970s, a shopping cart robot, governed by a computer the size of a living room, could meticulously trace a white line. During the 1980s, television cameras facilitated rudimentary stereo vision, allowing a robot to traverse a 30-meter obstacle course in 5 hours. By the year 2000, Moravec had constructed a robot capable of navigation utilizing photorealistic maps of its environment. This parallels the evolution from a slug to a small fish in the context of animal intelligence. The rapid increase in processing power enables the development of robots with functionality and intelligence comparable to that of small reptiles. Moravec predicts that artificial intelligence will attain human-level capabilities in approximately 20 years. In his book Mind Children, Moravec examines the ramifications of our current trajectory. He concurs with the more optimistic perspectives of science fiction, that humanity will be emancipated for creative and spiritual endeavors through the immense capabilities of machines. No longer constrained by the sluggish tempo of human cognition and the even more gradual process of biological evolution, intelligent machinery will manage its operations on an increasingly rapid and diminutive scale until coarse physical reality is transformed into refined, intentional thought. A dystopian interpretation of this future has been proposed by Bill Joy, the co-founder and chief scientist of Sun Microsystems. A significant number of future practical machines will be nanobots. They will observe the environment, rectify our ailments internally, and access locations inaccessible to humans. However, if they possess self-replicating capabilities, similar to miniature von Neumann probes, they could readily surpass natural organisms, and their exponential proliferation would dominate the planet. It is referred to as the gray goo dilemma. In our technological advancement, we are precariously positioned. Successfully navigating this phase, which may serve as the bottleneck that stifles numerous promising civilizations, will enable us to surpass the constraints of natural selection. Individuals familiar with computer challenges recognize that software advancements lag significantly behind hardware improvements. Nonetheless, if self-programming computers develop superior iterations of themselves, the advancement will hasten towards what Ray Kurzweil refers to as the singularity. He believes the singularity will confer immortality upon the consciousness of individual organisms. The characteristics of this transition are ambiguous. It could result in a solely computational future, wherein posthumans abandon biology and transform into disembodied thought collectives. It may also give rise to machine-human hybrids. We envision progressively bionic humans possessing skeletons composed of advanced composite materials, while their intricate organs, such as brains and eyes, remain biological. The transition may not be a unidirectional membrane. Posthumans can leverage their advanced abilities to transform biology, seamlessly transitioning between artificial and natural forms. These represent our potential futures. Within the expansive cosmic laboratory, the amalgamated potential of biology, engineering, and computation is virtually boundless. In the 1960s, Russian physicist Nikolai Kardashev theorized about the technological potential of advanced civilizations. A primitive civilization designated as K0 lacks control over the resources of its home planet. We are nearing K1 status, utilizing all local resources, approximately 1,012 watts. The energy we emit into space renders us inconspicuous at stellar distances. A K2 civilization harnesses the entirety of 1,026 watts from its star, potentially by constructing a hollow sphere around it, known as a Dyson sphere, named after physicist Freeman Dyson. The Earth absorbs a negligible fraction of the Sun's energy. Capturing the entirety of it for 1 second would satisfy global energy requirements for 1 million years. K3 civilizations are nearly unfathomable to us as they harness the complete resources of a galaxy. Considering the possibility that this could all be a mere illusion and that we may represent the pinnacle of advancement, how could these other civilizations traverse and communicate? K1s would employ technologies that are currently in nascent stages of development, including nuclear propulsion and laser sails. The favored communication method may involve particle beams composed of neutrinos or dark matter that propagate at the speed of light and encounter minimal resistance. The differences between travel and communication would become irrelevant. Teleportation could replicate conscious states or organisms at a distant location, transmitted by the swift propagation of electromagnetic waves. K2 engineers could utilize stars and communicate by orchestrating stellar cataclysms, such as supernovae and gamma-ray bursts, observable in distant galaxies. Should physics permit, K3 civilizations could achieve mastery over wormhole travel and communicate through the manipulation of space-time. Our radio pulses appear insignificant when we consider entities capable of emitting gravitational waves, generating nascent universes, and traversing the multiverse. Increasingly perplexing, in contemplating extraterrestrials capable of manipulating galaxies, we have transcended the realm of plausibility. As the Queen of Hearts advised Alice, at times, I have accepted as many as 6 implausible concepts before breakfast. Let us explore the potential entertainment of supercivilizations. What actions would a posthuman intelligence undertake with its extraordinary abilities? We are entirely ignorant, as we are to a worm. The forefront of our technology is apparent in video games, where we develop progressively advanced artificial realities. What is the extent to which simulations can be created? We may exist within a physical simulation created by a vastly superior civilization, akin to an advanced iteration of the film The Truman Show, where the unsuspecting protagonist inhabits a constructed reality beneath an artificial dome. Physicists can ascertain the energy necessary to simulate a specific size. Only a K3 civilization could create a comprehensive planet-scale simulation with diminished construction precision for areas of the solar system and beyond that remain largely uncharted. This scenario appears improbable due to the fantastical nature of harnessing a galaxy's energy. The notion that superintelligences might generate a computer simulation of consciousness is increasingly challenging to disregard. Contemplate the simulation hypothesis. Your existence occurs within a virtual reality generated by a computer created by an advanced civilization. Nick Bostrom contends that at least one of the subsequent propositions must be valid. Primarily, nearly all civilizations face extinction before achieving the capability to develop such a simulation. Secondly, almost no posthuman civilization opts to conduct simulations of minds akin to ours. The third assertion is that we are highly likely to reside in a simulation. This resembles the film The Matrix, albeit devoid of the implausible notion that an advanced civilization would require our brains as an energy source. Bostrom presents concepts such as the simulation hypothesis earnestly yet with a hint of amusement. His work combines whimsy with logical rigor. The argument hinges on substrate independence, the notion that consciousness can be instantiated equally in a silicon-based network, such as a computer, and a biological network, such as a brain or cranium. The prerequisites are significantly lower than those for developing a physical simulation. The computational capacity needed to replicate a human brain is 10 to the power of 17 operations per second. IBM is at the forefront of developing the first petaflop computer, capable of performing 10 to the 15th operations per second, which is merely 2 orders of magnitude below this standard. To replicate the complete mental history of humanity, referred to by Bostrom as an ancestor simulation, approximately 10 to the 35th power operations per second would be necessary. This endeavor would necessitate a computer of monumental proportions with current technology. However, advancements in quantum computing could enable the construction of a more compact device. Consequently, superintelligent civilizations would find ancestor simulations trivial to generate, enabling them to create an immense quantity of such simulations. The simulation hypothesis is not absurd. It is grounded in a simple extrapolation of our own comparatively limited technological abilities. According to Bostrom's assertions, if the initial proposition holds, then intelligent life in the universe is scarce, placing us on the brink of a critical juncture. Let us anticipate that this is incorrect. The second proposition cannot be assessed, as the recreational preferences of a super-civilization remain unknown. It suggests significant convergence in the motivations of advanced civilizations, if virtually none opt to simulate minds akin to ours. though this remains speculative. If even a minor percentage of them generate simulations, we are confronted with the ramifications of the third proposition. If the initial two propositions are false, it follows that there are likely numerous simulated minds compared to non-simulated minds operating within organic brains. According to the mediocrity principle, it is significantly more probable that your mind is simulated rather than one of the rare biological neural types. Negative. Upon reading this, an internal rebellion ensues. I exist. I am alive. I am aware of this moment. Apologies, but that demonstrates nothing. Individuals will perceive their lives as authentic rather than simulated, yet the majority will be mistaken. We could not ascertain that we exist within a simulation unless the simulators chose to disclose this information for their entertainment. Virtual reality remains nascent. However, those who have observed a teenager engrossed in the intricately designed environment of a role-playing video game can discern the trajectory of the technology. The reality you perceive is represented as electrical signals within your brain, which functions as an electrical network. An exceptionally advanced civilization could fabricate a world so intricately detailed that we would be unable to differentiate it from reality. What specific experiences did Alice encounter during her adventure? Was it a dream or a hallucination? And did she awaken at the conclusion? The simulation hypothesis presents intriguing challenges, including the potential for nested simulations. A simulated civilization akin to ours may generate its simulations, rendering it improbable that our simulators are genuine. The regression is not infinite, as this would necessitate boundless computational resources at the foundational level. It suggests solipsism. What if certain humans are simulated shadow individuals? If this is accurate, how can you ascertain that you are not the sole entity that is real among simulated beings? Or I? Consciousness enables us to confront the essence of reality, provided we dare to do so. In a classical Chinese narrative, three philosophers convene to sample vinegar, which represents the essence of life. The initial drinker is Confucius. It is acidic, he states. Buddha subsequently consumes a beverage. He articulates the vinegar as acrid. Lao Tzu is the final individual to experience the taste. He exclaims, "It is pristine." Sentience enables us to establish a connection with the universe in which we exist. Simplistically, there are three methods by which humans have sought to comprehend their position in the universe. They are not wholly separate, and numerous individuals opt to pursue multiple trajectories. They all embody vinegar. The initial aspect is science. Science represents a pinnacle of human intellectual achievement. We possess a manual detailing the functioning of the universe and the numerous interactions between matter and radiation. We have envisioned our intellect within the nucleus of an atom and traversed a cosmos comprising billions of galaxies. We narrated our history from the era of the nascent, heated universe through the formation of atoms and our evolution from primordial organic matter on a solitary planet illuminated by a protective star. The narrative is extraordinary, and we consider it to be authentic. However, science remains silent on the subject of meaning. The reason for the universe's existence and the capacity of specific atomic configurations to ponder their existence remains unknown. This scientific book contains compelling prose. However, it does not qualify as literature or a work of art. We will never pursue it and exclaim, "Indeed, that is the reason." More concerningly, science serves as a lens that amplifies our most admirable and deplorable traits. It can be utilized to eradicate disease and nourish the global population, or to annihilate one another and degrade the biosphere. In that regard, we possess free will. Subsequently, there exists an organized religion. Science and religion exist in a state of tension, particularly in the United States, where their interaction is frequently characterized by hostility. Religious adherents often perceive the absence of a creator and a purposeful design for the universe as a moral deficiency. They believe that all scientists are materialists and reductionists. Numerous individuals suggest that religion exists for evolutionary purposes and is entirely utilitarian in nature. Psychological Construct 24. Astrobiology poses a compelling challenge for theistic religions. All evidence suggests that we are part of a continuous spectrum of biological activity on this planet, with no distinguishing characteristics separating us from other advanced species, such as elephants and orcas. Religious individuals may reference faith, yet the assertion that animals lack spiritual dimensions remains unsubstantiated and, consequently, constitutes an act of faith itself. What we understand aligns with terrestrial biology as a singular instance of a broader array of biological forms in the universe. In the absence of evidence for extraterrestrial life, we may circumvent the matter. Nonetheless, the statistical evidence indicating the emergence of sentience elsewhere compels intrepid theologians to contemplate the ramifications. Do sentient extraterrestrials possess souls? Did Christ also die for their sins? What is their relationship with the hypothetical creator? Brother Guy Consolmagno, whom we previously encountered on the Antarctic ice in pursuit of meteorites, has authored a booklet titled Intelligent Life in the Universe: Catholic Doctrine and the Inquiry into Extraterrestrial Intelligent Life. He examines these inquiries and concludes that there is no issue for Catholicism regarding extraterrestrials. Holy Scripture contains no evidence to affirm or refute the existence of intelligent life beyond Earth, he states. Popular culture has transcended mere accommodation to amalgamate concepts of science and religion. In Steven Spielberg's 1977 film Close Encounters of the Third Kind, the alien spacecraft embodies a stark representation of an Old Testament deity. When Richard Dreyfuss is guided inside towards the conclusion, he assumes a cruciform posture. Numerous films since that time have employed extraterrestrials to narrate tales of morality, including themes of virtue and vice, condemnation and salvation. 5 years later, Spielberg presented his interpretation of the New Testament with the iconic E.T. In that film, a subtly disguised allegory of the narrative of Christ, the extraterrestrial embodies a childlike innocence and possesses the ability to heal. Extraterrestrial is misconstrued, persecuted, slain, and subsequently resurrected. Extraterrestrials represent a contemporary belief system, serving as conduits for our anxieties and desires. The third avenue is spirituality. The term is delightfully ambiguous, sufficiently expansive to imply metaphysics, while devoid of the encumbrances associated with traditional religions. 2/3 of scientists identify as strongly or somewhat spiritual. The concept of spirituality also encompasses non-theistic religions such as Buddhism, which features a central theme of interconnectedness that superficially aligns with contemporary scientific findings. Is this a genuine commonality, or merely flawed reasoning and optimistic conjecture? Let us streamline the discourse by condensing the Trinity into a duality. Niels Bohr stated, "A profound truth is one whose antithesis is also a profound truth." What insights does astrobiology provide regarding our possible isolation? We might be solitary. The contingencies of evolution may be so predominant that the emergence of large brains is exceedingly improbable, and intelligence so uncommon that we exist in isolation both temporally and spatially. Alternatively, we may be the initial ones. We would certainly be exceptional. However, solace in that fact can only be found within the framework of a religious tradition. The empirical realities of science indicate that our aspirations and cherished values are merely the byproducts of chance and accident. We might not be solitary. In this instance, the options proliferate. Our biology may exemplify a universal solution to the organization of matter, indicating a kinship with organisms throughout the cosmos, defined by attributes such as DNA, function, and form. This cannot be dismissed, yet it reflects constrained reasoning. Undoubtedly, they exist, and they must resemble us. English astrophysicist Arthur Eddington stated, "The universe is not only stranger than we conceive, it is stranger than we can conceive." Other life forms may possess such advanced capabilities that we are rendered inconsequential. Our religions would consequently be mere constructs of ego, as anthropocentric as the alien iconography of Star Wars. In contrast to Brother Consolmagno's assurance that Christianity could include extraterrestrial beings, reflect on the sentiments of American patriot Thomas Paine in The Age of Reason. To believe that God created a multitude of worlds, at least as numerous as the stars, diminishes the Christian faith to a state of insignificance and absurdity, dispersing it in the mind like feathers in the wind. Extraterrestrial life may be so peculiar that communication is infeasible, or so unusual that it remains unidentifiable. We may be mere instruments of a superior species that disseminated life on Earth 4 billion years ago. In other biological contexts, communal solutions may be employed, facilitating the sharing of both senses and perceptions, thereby isolating us with our enclosed minds and contemplative thoughts. Consciousness, for lack of a more suitable term, may manifest at the cellular level, comparable to the size of a pinhead, or over vast epochs and across the expanse of galaxies. The esteemed mystics of the world have articulated the tension between being and nothingness, as well as self and other. In the initial sutra of the Siddha yogic tradition, consciousness is the origin of the universe, just as the universe is the origin of consciousness. The skeptic may deem this solipsism as absurd as the simulation hypothesis. However, the scientific explanation of creation is equally extraordinary. It asserts that all the trillions of habitable worlds in the universe, along with their potential and actual life forms, originated from an infinitesimal point of space-time, a minute quantum possibility. In Albert Camus' novel The Stranger, the young Algerian man Meursault navigates his existence in a state of detachment. He exists entirely in the present, his actions impulsive and devoid of any overarching strategy. He murders a man without discernible motive. Ultimately, he confronts the guillotine. Camus' existential parable is composed in a terse and disquieting manner. We have a profound need to create meaning in our lives. Indeed, that differentiates us from bees or termites, with their inherent industriousness and genetically programmed behavior. Science consistently attributes no particular importance to our existence. To attain relief from what Camus termed the benign indifference of the universe, we must introspect. Astrobiology is a nascent field. The complete narrative of life on Earth remains elusive, as the exploration of the solar system is still in its nascent stages, and we have yet to delve into the habitable planets beyond. We may ascertain whether we are unique or merely a footnote in the extensive biological history of the outer region of the Orion arm of the spiral galaxy known as the Milky Way. Science is in its infancy. We have recently acknowledged our position in the universe. We are fully justified in being astonished by our level of knowledge. In A Brief History of Time, Stephen Hawking inquires, "What instills vitality into the equations and generates a universe for them to delineate?" We continue to grapple with the inquiry presented by Blaise Pascal 350 years ago. Why is there something rather than nothing? Humans are youthful. While capable of remarkable acts of beauty and kindness, we are also collectively aggressive and myopic. Intelligence alone will not guarantee our survival if technology surpasses wisdom. Fearful of our mortality, we send messages into the expansive cosmos and ponder our solitude. Our utmost endeavor is to generate significance with every breath, each unique thought, and every act of compassion or love. We must cherish both our science and our art, as they bring us joy and fulfillment.